Welcome! In this session, we'll dive into the problem number 674, longest continuous increasing subsequence. We'll explore the problem statement, examine various approaches, and work through the solution together. Let's get started. In this problem, we're tasked with finding the length of the longest continuous increasing subsequence, or LCIS, within an unsorted array of integers called nums. A subsequence here refers to a sequence derived from the array where elements are not rearranged, and some elements may be deleted, but the original order is preserved. For the subsequence to be considered continuous and increasing, it must have each element strictly greater than the one before it, and all elements in the subsequence must appear consecutively in the array without any gaps or skips. Our goal is to determine the length of this LCIS. If the input array doesn't contain any increasing subsequence, we simply return 0. The input will be an array of integers, which may even be empty, and the output will be a single integer that represents the length of the longest continuous increasing subsequence. Let's look at some examples to better understand the problem. In the first example, the input array is 1, 3, 5, 4, 7. The longest continuous increasing subsequence in this array is 1, 3, 5. This subsequence has a length of 3, and it satisfies the strictly increasing condition, as each number is greater than the one before it. While 4, 7 is another increasing subsequence, its length is only 2, so it's not the longest. Therefore, the output for this example is 3. In the second example, the input array is 2, 2, 2, 2, 2. Here, all the elements are the same, so there isn't any increasing subsequence. The longest continuous increasing subsequence in this case is any single element, and its length is 1. For the third example, the input array is empty, represented by. Since the array contains no elements, it's impossible to have an increasing subsequence, so the output in this case is 0. These examples show how the constraints of the problem apply to different scenarios, including arrays with duplicates and empty arrays. Now, let's consider the constraints and edge cases for this problem. First, the length of the input array can range from 0 to 10,000 elements, meaning the solution must handle both very small and very large arrays efficiently. Each integer in the array can range from -1 billion to 1 billion. For edge cases, if the array is empty, the output should be 0 since no subsequence exists. If all elements in the array are identical, the longest subsequence will consist of just a single element, resulting in an output of 1. Finally, if the entire array is strictly increasing, the LCIS will span the entire length of the array, and the output will simply be the size of the array. Keeping these constraints in mind is crucial for designing an efficient and robust solution to the problem. To begin solving the problem, one of the first approaches we can consider is the brute force method. The intuition here is to examine every possible subarray within the input array nums and check if each subarray is a continuous increasing subsequence. To do this, we would compare every adjacent pair of elements in the subarray and ensure that each element is strictly less than the next. Once we identify a valid subsequence, we calculate its length, and we keep track of the longest subsequence found so far. While this method is straightforward and easy to understand, its implementation involves 3 nested loops, 2 to generate all possible subarrays and 1 to verify the increasing condition. This leads to a time complexity of O(n) cubed, which becomes computationally expensive for large arrays. On the bright side, it has low space complexity, requiring no additional data structures. However, the high time complexity makes it impractical for larger inputs, so we need a more efficient approach. To improve upon the brute force approach, we can use an optimized sliding window technique. The core idea is to iterate through the array only once while keeping track of the length of the current continuous increasing subsequence. As we traverse the array, we compare each element with the previous one. If the current element is greater than the previous, we extend the subsequence by incrementing its length. If the condition is broken, that is, the current element is not greater than the previous one, we compare the length of the current subsequence with our maximum length seen so far and reset the current subsequence length to 1. This approach avoids the need to check all possible subarrays, making it significantly more efficient. By leveraging this single-pass logic, we reduce the time complexity to O(n), as each element is processed only once. Additionally, we use only a few variables to track the lengths, so the space complexity is O(1), making this approach both time and space efficient. The sliding window approach is highly efficient, with a time complexity of O(n), because we traverse the input array exactly once. It also requires only constant space, as we only utilize a few variables to store intermediate results like the maximum and current subsequence lengths. This makes it an excellent choice for this problem. However, for completeness, another potential approach is the dynamic programming method. Here, we define a DP array where each element dp, I, represents the length of the longest continuous increasing subsequence ending at index I. The recurrence relation is straightforward. If the current element is greater than the previous one, we extend the subsequence by setting dp, I, equals dp, I1, plus 1. Otherwise, we start a new subsequence, setting dp, I, equals 1. While this approach is easy to implement and also has a time complexity of O(n), it requires additional space for the DP array, making it slightly less optimal than the sliding window technique. To complete the dynamic programming solution, we calculate the final result by simply taking the maximum value from the DP array. While this approach is efficient in terms of time complexity, with O(n), due to the single traversal of the array, its space complexity is O(n), because we need to maintain the DP array throughout the computation. This extra space requirement is the main drawback of the dynamic programming method when compared to the sliding window approach, which achieves the same time complexity but with constant space. After evaluating all methods, the sliding window technique stands out as the most efficient overall. It avoids the computational overhead of the brute force method and the additional memory usage of dynamic programming, making it the ideal solution to this problem. When comparing all three methods, we see clear trade-offs. The brute force approach is conceptually simple but suffers from an impractical time complexity of O(n cubed, making it unsuitable for large inputs. The dynamic programming approach improves on time efficiency, requiring only O(n), but it introduces additional space usage with an O(n) DP array. The sliding window approach, on the other hand, achieves the best of both worlds. It matches the time efficiency of dynamic programming while maintaining a constant space complexity of O(1). This makes it the most efficient solution overall, as it balances both time and space considerations. By prioritizing efficiency, the sliding window approach emerges as the optimal strategy for solving the longest continuous increasing subsequence problem. In this problem, the objective is to determine the length of the longest continuous increasing subsequence, or LCIS, within a given array nums. Here, a continuous increasing subsequence is defined as a sequence of adjacent elements in the array where every element is strictly less than the one that follows it. To begin solving this problem using the brute force approach, we start by initializing two key variables. The first is max_length, which will store the length of the longest LCIS found so far, and this is initially set to 0. The second is n, which represents the length of the input array for clarity. Next, we use nested loops to evaluate all possible subarrays. The outer loop selects the starting index I for each subarray, while the inner loop iterates through potential ending indices j, beginning from I. This ensures we examine every possible subarray within nums. For each subarray, we then check if it satisfies the condition that all adjacent elements are strictly increasing, meaning nums k plus 1, for every index k between I and j1. At this point, we compare the calculated length with the current max_length. If the subarray's length is greater, we update max_length accordingly. Once all subarrays have been evaluated, the value of max_length will represent the length of the longest continuous increasing subsequence, which is what we return as the final result. If this condition holds true for a subarray, we calculate its length as j I plus 1. Now, although this approach is thorough, it's important to recognize that it is computationally expensive. The brute force method involves iterating over all possible subarrays and performing checks for each one, resulting in a time complexity of O(n cubed. This highlights an opportunity for optimization. Instead of examining every subarray individually, we can adopt a single-pass approach to dynamically track the length of increasing sequences as we iterate through the array. This optimization reduces the time complexity to O(n), making it far more efficient for larger arrays. Additionally, it's crucial to consider edge cases such as an empty array, single-element arrays, or cases where no increasing subsequence exists. Edge cases play a significant role in ensuring the robustness of our solution.
For example, if the input array is empty, the result should simply be 0 since there are no elements to form any subsequence.
In the case of a single element array, the output would be 1, as the single element itself is the LCIS.
If all elements in the array are equal, there is no increasing subsequence, so the result would also be 1. On the other hand, if the array is already sorted in ascending order, the LCIS is the entire array, and its length is equal to the length of the array.
From an implementation perspective, the brute force approach primarily relies on keeping track of two variables, max_length to store the length of the longest LCIS and n to represent the size of the input array. These variables, along with the input array nums, allow us to systematically explore all subarrays.
Let's examine the Python implementation of this approach. The function findLength of LCIS begins by calculating the length of the array and initializing max_length to 0.
The outer loop runs through all starting indices, and the inner loop evaluates all ending indices for subarrays starting at each outer loop index.
Within the inner loop, we perform a check to determine whether the current subarray is strictly increasing.
This check is done using another loop, where we compare each adjacent pair of elements within the subarray. If we find any pair where the condition nums k plus 1 does not hold, we set a flag as _increasing to false and break out of the loop. If, however, the flag remains true after checking all adjacent pairs in the subarray, we know the subarray is strictly increasing. At this point, we calculate its length and update max_length if the current subarray's length is greater than the previous maximum. Once all subarrays have been evaluated, we return max_length as the final result. While this implementation is clear and exhaustive, its n³ time complexity makes it impractical for large input sizes. To address this inefficiency, we can adopt an optimized approach based on the sliding window or single pass technique. This method eliminates the need to evaluate all subarrays by dynamically keeping track of the length of the current increasing subsequence during a single traversal of the array. This drastically reduces the time complexity to n, making the solution much more scalable. When comparing the two approaches, the brute force method has a time complexity of n³, due to the nested loops and repeated checks for each subarray. However, it has a space complexity of 1, since it doesn't require any additional data structures. In contrast, the optimized approach also has a space complexity of 1, but achieves a significant improvement in time complexity, reducing it to n, by examining the array in a single pass. This makes it a far better choice for handling larger input sizes, such as arrays with up to 10,000 elements. The key takeaway here is that while the brute force method offers a comprehensive and simple solution, it's computationally expensive and unsuitable for larger datasets. The optimized single-pass algorithm not only improves efficiency but also preserves the clarity of the solution, making it the preferred approach in most scenarios. By understanding both methods, we gain insights into how algorithms can evolve from a straightforward brute force technique to an efficient, scalable solution through careful optimization. Let's break down the solution for LeetCode problem number 674, longest continuous increasing subsequence. The function findLength of LCIS takes an input list nums and returns the length of the longest continuous increasing subsequence, LCIS. ###explanation. 1. Handle edge case. If the input list nums is empty, we immediately return 0 because there are no subsequences to consider. 2. Initialize variables. Max_length is initialized to 1 to track the maximum length of any LCIS found so far. Current_length is also initialized to 1 to track the length of the current increasing subsequence as we iterate through the array. 3. Iterate through array. We start from the second element, index 1, and compare each element with the previous one. If the current element is greater than the previous one, it means the sequence is still increasing. In this case, we increment current_length and update max_length if current_length exceeds it. If the sequence breaks, i.e., the current element is not greater than the previous one, we reset current_length to 1. 4. Return the result. After processing all elements, max_length contains the length of the longest continuous increasing subsequence. ### complexity. Time complexity, n, where n is the length of the input array. We iterate through the array once. Space complexity, 1, as we use only constant extra space. This solution efficiently handles all edge cases, including empty arrays and arrays with no increasing subsequences. This is the Java implementation of the longest continuous increasing subsequence problem. The logic mirrors the Python implementation but utilizes Java-specific constructs, such as the math.max method for updating the maximum length and explicit handling of array null checks. The method iterates through the input array, comparing consecutive elements, and calculates the length of the longest continuous increasing subsequence. The algorithm runs in O(n) time complexity. Here, we have the input array nums equals 1, 3, 5, 7. First, we initialize two variables, max_length and current_length, both set to 1. These will help us track the length of the longest increasing subsequence and the length of the current sequence, respectively. Starting the iteration, we compare the second element, 3, with the first, 1. Since 3 is greater than 1, it means the sequence is still increasing, so we increment current_length to 2. At this point, we update max_length to the maximum of its current value and current_length, which becomes 2. Next, we compare 5 with the previous element, 3. Again, since 5 is greater than 3, the sequence remains increasing, so we increment current_length to 3 and update max_length to 3. Finally, comparing 7 with 5, we see that the sequence continues to increase, so current_length becomes 4 and max_length is updated to 4. After completing the iteration, we return max_length, which is 4, as the length of the longest continuous increasing subsequence. In this example, the input array is nums equals 2, 2, 2, 2. We again initialize max_length and current_length to 1. Now, as we start iterating, we compare the second element, 2, with the first, which is also 2. Since 2 is not greater than 2, the sequence is no longer increasing, so we reset current_length back to 1. There's no need to update max_length since it remains 1. Moving to the next comparison, we look at the third 2 and compare it with the second 2. Again, the sequence is not increasing, so we reset current_length to 1 without changing max_length. Finally, we compare the fourth 2 with the third 2, and the same condition holds, current_length stays at 1, and max_length remains unchanged at 1. At the end of the loop, we return max_length, which is 1, as there is no increasing subsequence in this array. Here, we have a partially increasing sequence with input nums equals 1, 3, 5, 4, 7. As always, we initialize max_length and current_length to 1. Starting the iteration, we compare 3 with 1. Since 3 is greater, the sequence is increasing, so we increment current_length to 2 and update max_length to 2. Next, we compare 5 with 3. As 5 is greater, the sequence continues to increase, so we increment current_length to 3 and update max_length to 3. However, when we compare 4 with 5, we see that 4 is not greater, meaning the sequence is no longer increasing. At this point, we reset current_length to 1 while leaving max_length unchanged at 3. Finally, comparing 7 with 4, we see that 7 is greater, so we increment current_length to 2. However, max_length remains 3, as the current subsequence is shorter than the previous longest one. At the end of the loop, we return max_length, which is 3, as the length of the longest continuous increasing subsequence. To summarize, the algorithm works by tracking current_length for the ongoing increasing subsequence and updating max_length whenever a longer subsequence is found. If the sequence becomes non-increasing at any point, current_length is reset to 1. This ensures that we only count continuous increasing subsequences. The result, stored in max_length, is the maximum value encountered during the traversal of the array. This approach efficiently determines the length of the longest continuous increasing subsequence in a single pass through the array. The time complexity of our solution is O(n), where n is the size of the input array. This is because the algorithm processes the array in a single pass using a simple for loop. Starting from the second element, it performs n1 iterations, where each iteration involves a series of constant time operations. These operations include comparing the current element with the previous one, updating the current length of the increasing subsequence, and recalculating the maximum length using the max function. Since all these steps are O(1) operations, the total time complexity becomes O(n*(O)(1), which simplifies to O(n). This holds true for all cases: the best case, where the array is strictly increasing; the worst case, where the sequence alternates frequently; and the average case, where we still examine each element in linear time. The space complexity of this solution is O(1), which means it uses a constant amount of extra memory, regardless of the size of the input array. The algorithm only requires two integer variables, max_length to track the longest subsequence found so far, and current_length to track the length of the current subsequence being evaluated. Both of these require fixed memory space. Additionally, the loop variable also uses a constant amount of memory. Importantly, no extra data structures are created, and the input array is accessed in a read-only manner without any modifications. This ensures that the auxiliary memory usage remains minimal and independent of the input size. If we compare this optimized approach to a brute force solution, the efficiency becomes even clearer. A brute force method would involve generating all possible subarrays to evaluate their continuity and length. Generating these subarrays would take O(n)² time, and checking each one would add another O(n) for each subarray. This results in a total time complexity of O(n)², which simplifies to O(n)³. In contrast, our optimized approach uses a sliding window technique to traverse the array in a single pass, updating the lengths dynamically. This reduces the time complexity to O(n) and the space complexity to O(1), making it significantly faster and more memory efficient than the brute force method. To confirm the efficiency of the optimized solution, we can look at the mathematical proof for its big O analysis. For time complexity, the outer loop executes n1 times, and each iteration involves constant time operations like comparisons and updates. Multiplying these together gives us n1*(O1), which simplifies to O(n). For space complexity, the algorithm only uses a constant amount of memory for variables like max_length, current_length, and the loop index. Since none of these depend on the input size, the space complexity is O(1). This proves that the solution achieves the most efficient time and space complexity possible for this problem, making it optimal for a wide range of input sizes. One common mistake to watch out for is confusing subsequences with subarrays. Remember, a subarray is always a contiguous segment of the array, while a subsequence can skip elements. Misunderstanding this distinction can cause your solution to fail, so it's important to confirm whether the problem specifies subarrays. Another frequent issue is overlooking edge cases. For example, you need to handle scenarios like empty arrays, single-element arrays, or arrays where every element is identical. Ignoring these can result in runtime errors or incorrect outputs, so thorough testing is essential. Additionally, relying on a brute force approach can be problematic, especially for larger inputs. Generating all possible subarrays results in time complexities like O(n)³ or O(n)², which are impractical for constraints where n could go up to 10,000. Instead, you should focus on more efficient techniques like sliding windows or dynamic programming. Also, pay close attention to comparison logic. For instance, when checking for increasing sequences, ensure you're using the right operators, whether strict inequality like nums, i+1, or non-strict inequality, depending on the problem's requirements. Lastly, when using a sliding window approach, don't forget to reset your variables, such as the starting index, whenever the sequence breaks. Neglecting to reset state can lead to incorrect results even with an otherwise correct algorithm. Now, let's consider some insights for interviews. First, it's crucial to understand the problem constraints. Interviewers often evaluate not just your ability to solve the problem, but also your handling of edge cases and efficiency with large inputs. So, clarify the constraints and expectations before jumping into the solution. Scalability is another key factor. If the brute force method is too slow, explore more efficient techniques like sliding windows, two-pointer strategies, or dynamic programming. When discussing your approach, clearly explain the trade-offs. For example, you could mention that while a sliding window reduces time complexity, it might require additional variables to track state. Pattern recognition is also helpful here. This problem falls under the broader category of sequence problems, so understanding its similarities to challenges like longest increasing subsequence or maximum sum subarray can help you leverage existing strategies. Speaking of related problems, you might encounter variations like LeetCode 300 for the longest increasing subsequence, LeetCode 53 for maximum subarray, or LeetCode 209 for minimum size subarray sum. Recognizing these connections can make it easier to transfer techniques and adapt to new problems. Finally, let's touch on alternative approaches and the trade-offs involved. The sliding window method is a highly efficient approach with O(n) time complexity. By maintaining a window of valid elements using 2 pointers, it avoids redundant computation. However, you need to carefully manage the window boundaries to ensure correctness. Dynamic programming is another option, where you use a DP array to store the length of the longest subsequence ending at each index. This method is often more intuitive, but it comes at the cost of O(n) extra space. For variations like the longest increasing subsequence, binary search can be an excellent optimization. By combining binary search with a greedy strategy, you can achieve O(n log n) time complexity. That said, it's more complex to implement and isn't suitable for all variations of sequence problems. A few key insights to keep in mind: always clarify whether the problem involves subarrays, subsequences, or other sequence types. Make sure to account for edge cases and input constraints up front to avoid surprises. Finally, adopt an iterative optimization process. Start with a straightforward brute force solution, then refine your approach step by step to improve efficiency and clarity. Great job! To wrap up, we reviewed key points from the problem, including the efficient solution and its complexity. Remember the takeaways, such as starting with intuition and using techniques like sliding windows for subarray problems. Thanks for watching, and we hope to see you in future sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!